Okay, so this lab is going to allow you to measure centripetal force, centripetal acceleration, velocity, all that good stuff. So the first thing you need is a piece of string about yay long, okay? Not precise, yay long. So then you need to very securely tie a rubber stopper to the end of it. I've got a tub with a whole bunch of different size rubber stoppers. I suggest on the first trials you choose like a medium-sized stopper. So, not a big deal, boom, tie that onto it. Make sure that it's tied securely. You don't want this thing turning into a projectile. That would be bad. So, got that tied. Now, the next thing you're going to need is a glass tube. So, when you, the glass tube, a lot of these will have like a smoother edge and a rougher edge. Make sure that you pick the one that has a smoother edge that's going to be on top, because what's going to happen is that string is going to rotate around that edge, and if it's rough, then it tends to cut through it. So make sure that you choose the smoother edge to be on top. Feed that through, boom. Then just tie a simple knot at the bottom. Make the squirrel run back to the tree. Then make the squirrel run around the tree. And then make the squirrel dive through the hole into the tree. And you get a nice little loop like that. So, on the first trials, I tell you which masses that you're going to hang. So on this data sheet, I tell you you're going to hang 0.1, 0.2, 0.3. So let's start with 200 grams. So you got a 200 gram mass. So here's the basic idea. This is why it's called like the cowboy cowgirl lab. As you get this spinning, you can reach a point of equilibrium where that mass is suspended. Now, if I change the conditions, okay, I can make it go further up. If I slow it down, I could establish a new equilibrium, okay? So depending on how fast you spin it, that changes the radius of the swing, okay? So if you look at what you can measure, as that thing goes around, here's the rubber stopper as it swings around. So here's the main assumption that you're going to make at the beginning of the lab. What you're going to assume is that here's this tube. In this case, you have a 0.2 kilogram mass. The key assumption that we're going to make at the beginning is that whatever the weight is that's hanging down, like this, whatever that weight is that's hanging down, is whatever the centripetal force is, okay? So that's it, because there has to be something creating that inward force to keep it moving in a circle, okay? So instead of holding it like this, and I can just let my hand do it, but my hand sucks as far as like trying to measure stuff. But what I'm going to do is I'm just going to let gravity pulling down on this create the inward force to keep the rubber stopper moving around in a circle. So over here on that column, like for example on this 200 gram mass, 0.2 kilograms, the centripetal force, if I take 0.2 times 9.8 meters per second squared, you get 1.96 newtons. So on this second trial, where you're going to use 0.2 kilograms, and that column where it says centripetal force, you're going to put 1.96 newtons. If it's 0.1, you're going to take that times 9.8. 0.3, 0.4, whatever. So the centripetal force column is whatever the mass of what's hanging down, not the mass of the stopper. The mass of whatever hanging down multiplied by your gravitational acceleration, that's going to be your centripetal force. Okay? That's it. Now, this is where this becomes very much a group effort. Okay, so this is literally, I want you all to kind of work as one big group. So what's going to happen is that there's a couple of things. On the first one, I also tell you what radius that you're going to use. So to get that radius, here's what you've got to do. It's going to be a little bit tough to measure the radius if it's already spinning. Okay? So if this is going around like this, and I said, hey, Caitlin, measure the radius, that's going to be a little bit tough to do. Okay? Somebody's going to get hit with a rubber stopper. Bad things are going to happen.
I have a question.
So what?
What if we just catch it, stop it in that instant?
No.
No? Okay.
What if we pinch the string at the bottom?
Shh, just don't.
Wait.
Shh, stop. Okay.
These are good ideas.
So here's what you're going to do. You're going to measure out from the center mass of the stopper to the edge of the tube. Okay? So you're going to measure from here to the edge of the tube, 0.8 meters. Now, here's the tricky part. This is going to be from here to here, that's 0.8. But then what you're going to do is you're going to take a marker and you're going to put a mark on the bottom side of the string. The reason that you do that is that who's ever swinging the rubber stopper around, okay, when they're like this, and there's that mark. So I know when I get that mark up to the bottom of the tube, I know that this distance up here, so if I'm like this, and I have that mark there at the bottom, I know this distance is 0.8 meters. Okay, does that make sense?
Yeah.
So measure here on the top, but put the mark at the bottom. So when the mark gets here, that's 0.8. Don't put the mark at 0.8. Put the mark at the bottom of the tube.
Yes, Sensei.
Okay? Got that. So here's what you're going to do. You're going to get this thing going. You have your radius of 0.8 meters. So what you're going to do is that you're going to count 10 revolutions. You're going to time it. Okay? Now, this lab, mathematically, is a home run. Oddly enough, the most difficult part of this is timing correctly 10 revolutions. And I think Burkamp, seriously. No. If your data goes south, it's because who's ever timing can't time 10 revolutions. So let's talk about how this is going to work. Number one, you want at least 2 people timing this. At least 2, if not 3. Because if the data is wrong, the lab goes south. So you want to do 10 revolutions. So there's a couple of things about lab protocol on here. Number one, you're going to get this thing going. You're going to get it stable. You want that swinging in a horizontal plane like this. You don't want anything like this where it's going like this, okay? No, bad. You want it completely in a horizontal plane like this, okay? So, you're going to get it stabilized. You're going to have 2 people counting this. When you do this, you have to count 10 complete revolutions. So, what you're going to do is you're going to start it, go boom. But then, you're going to start it, but then you're going to go 1. So, you're going to start it, and then you're going to count 1. Okay? Don't start it and go, oh, that's 1. So, you're going to be going like this. Okay? You're going to start the timer, bam, 1, 2, 3, 4. Okay? Now, the other thing, do not count out loud. We all know you can count to 10. Because what's going to happen is that you're going to have other people in your group trying to time this as well. And if you're counting out loud, it's going to screw up everybody else. So do the guppy count. Okay, look like a little guppy in a fishbowl. Okay? Do not count out loud. Because other people in your group will go, shut up! Quit counting out loud. Because it's just going to screw up everybody. So, now, how you do the 10. What some people like to do is that they will pick a point like in the room. And so they're gonna be here like this, and like you're gonna pick a point, like maybe like those blue tubs in the back. So every time it crosses those blue tubs, that's a revolution. So I'd go 1, 2, 3, 4, every time it crosses up. Pick something in the room. If you really want to go hardcore, and I found this to be the best timing, you're actually going to like lay on the floor and then watch it go around like this, and you're going to pick like a seam in the ceiling and go, okay, boom, 1, 2, 3, 4, all right? So if that's what you want to do, lay on the floor, count it that way. Pick a point on the room, go like that. If your times are off, it's because somebody can't count to 10. Don't just say, oh, we'll take the average. No, somebody can't count to 10. Okay? Now, I'm going to tell you straight up, the hardest one to do is going to be that 400 gram mass. Mainly because of the fact that when I hook these together, and yes, you can hook them together like this. So now what's happening is that you have a lot of weight. You have a lot of weight hanging down. So to make that work, that has to go really, really fast. Okay? So the hardest one to get the good data on is that last one, because you have so much centripetal force hanging down that you have to go really, really fast, which means it's difficult to count. Okay? So I'm just telling you, that's the hardest one to do.
So are we only doing 4 different masses, or are we doing 12?
Oh, you're doing a total of 12 trials, but we'll talk.
We're only doing 1 through 4 as of now.
Gavin, why would you do that?
His eyes were closed.
It's okay. You let me worry about Louise.
I just thought it was funny.
Okay,
So good.
so this lab is brought to you by the equation centripetal force equals mass v squared r mv squared over r. And velocity is 2 pi r over t. So, listen to me very, very carefully. You have 3 variables that you're going to manipulate. Centripetal force, radius, and mass of the stopper. At any given instant, you're going to keep 2 of them constant, change the other one, and look at the impact that it has on velocity. So, on trials 1 through 4, you're making centripetal force get bigger and bigger and bigger because you're hanging more and more weight from the bottom of the string. So you're making a bigger and bigger centripetal force. Now, this is the mass of the stopper. The mass of the stopper is going to be the same on all 4 trials. That's a number. Okay? Main point being that the mass of the radius is a constant on trials 1 through 4. The radius is a constant. That's going to stay the same at 0.8. So mathematically, if you think about this, you can go, okay, right.
We're doing this as a group.
Yes. So that's going to be m over r. So this is a constant because if you take the mass, I'm not telling you you have to do this, I just need you to understand the mathematical concept of it. If you take the mass of the stopper and divide it by the radius, that's just some constant of proportionality. Okay, on 1 through 4, that ratio of mass of the stopper to radius is a fixed value. It's just some k. So then you got centripetal force equals kv squared. Okay, that's what you've got. Now, all this is, if you were in math class, you'd say, okay, hey, y equals kx squared. What's that graph going to look like?
Quadratic.
It's quadratic. Okay, you have some constant of proportionality. You have v squared. So you have y equals kv squared. That's all you got. So here's the deal. You don't need to find the value of k. You just need to know that it's a constant of proportionality. So here's the question. Louise, if I make the centripetal force bigger, what has to happen to my velocity to balance this out? Is it going to get bigger or smaller?
Bigger.
Bigger. But will it get bigger in a 1-to-1 ratio? Why not?
Because linear squares and linear square.
Beautiful. Since that velocity is squared. So the general relationship is there is a direct relationship between the centripetal force and the velocity. But it's not going to be linear because you have velocity squared. So anytime you see something squared, square root, cubed, anything like that, it can't be a linear function. Okay?
See,
So here's the point. So Louise just said as that centripetal force gets bigger, your velocity has to get bigger because your mass and radius are constants. So think about how that plays out in terms of velocity in 2 pi r over t. So on trials 1 through 4, you're going to keep the same radius. Top number is going to stay the same. So what's going to happen to the value of t to create a bigger velocity? Will it get bigger or smaller? Smaller. It's going to take less time. So what you should see as a trend, so on that total time column, that's going to be the time for 10 revolutions. The period, the second column over, that's the time for 1 revolution. So if you have the time for 10 revolutions, how are you going to get the time for 1 revolution?
Division.
Do not make this difficult.
What was the question?
Reciprocal.
what's the question?
If it takes, let's say it takes 14.6 seconds to make 10 revolutions.
Divided by 10.
How long does it take to make 1 revolution?
1.46.
Yeah, just divide by 10.
1.46.
Beautiful. Okay? So to get the column that says period, take the total time and divide that by 10. So on trials 1 through 4, what you should see is that the time is becoming smaller because you're increasing the centripetal force. Therefore, the velocity has to get bigger. The only way that you can create a bigger velocity is if you divide by a smaller value of t. Okay? Does that make sense?
Yes, that's it.
Got it. Cool. Now, here's the next thing. So over here on page 2, so let me kind of get you started on how I want these done. You're going to end up making a total of 3 different graphs for each of these sections. So on trials 1 through 4, you're going to draw a graph, and you're going to put velocity on the x-axis, and you're going to put centripetal force on the y-axis. Now I tell you, 2 of these graphs are going to start at 0, 0. This is one of them. Because if I don't have any velocity, I don't have any centripetal force. Okay? So this graph should look something like this when you get done. When you plot your data, let's say that you've kind of got this nice quadratic curve for 3 of the points, but you've got like a weird outlier. Go back and redo that trial. Somebody screwed something up on that trial. Okay? So you should see a trend. Now you're only basing it off 4 data points, but you should be able to see the trend. So when you answer question number 2, says you have this equation, F equals mv squared over r. Which variables were held constant and which variables were changed? So you have this centripetal force equals mv squared over r. Which 2 variables did you hold constant?
Mass and radius.
Yeah, so this is going to be the mass, so there's your answer. Which variables did you were constant? Mass and radius. So therefore, which variables changed?
Velocity and force.
Centripetal force and velocity.
Velocity.
Okay, boom, there you go. So when you get to number 3, on the basis of your graph, what's the relationship between velocity and centripetal force? Okay, the answer to none of those are linear. You can say it's direct with like velocity squared. You can say it's a quadratic relationship. Something. It's not going to be linear. Now, let me show you what I want done on number 4. So number 4, it says, hey, F equals mv squared. Simplify the equation in terms of a general mathematical equation. So this is what I'm looking for on number 4. You have centripetal force equals mass v squared over r. So this mass and radius are constants, okay? That's what you're saying. So what you can do then is just what I'd had up there. So since that ratio of the mass of the stopper to the radius is a fixed value, it's not going to change. That's just some constant. So all you have to say, and this is the easiest one, and you say, oh, that centripetal force equals k v squared. So this is why you graph it the way you do. This is why you put centripetal force on the y-axis and why you put velocity on the x-axis, okay? Because it has the general form of y equals kx squared. So that's why we plot centripetal force there, why we put velocity on the x-axis, okay? Makes sense. Now, then it says, explain the results of your graph. Here's what I'm looking for when you answer question number 4, when you explain the results of the graph. Listen to me very carefully. You want to mention all 4 of these variables. You want to mention centripetal force, mass of the stopper, radius, and velocity. So let me give you an idea of what I'm looking for. So one option is that you talk first about what's held constant. You can say, okay, since mass and radius are constant, then a bigger centripetal force requires a bigger velocity. Okay? Yeah, I've mentioned all 4 variables. I talked about mass and radius because those were constant. Then I said, oh, okay. Then as centripetal force increases, velocity has to increase. That's an option. Here's your other option. But wait, there's more. You could say, as centripetal force increases, velocity has to increase because mass and radius are constant. So basically, it's just how you want to sequence it. Do you want to talk about what's constant first and then talk about the 2 variables that change? Or do you want to talk about the variables that change first and then talk about what's constant? Okay, I don't care. But make sure on questions 4, 8, and 12 that you mention all 4 variables: centripetal force, mass, radius, and velocity. Make sure all 4 are mentioned. Okay? Now, so in 1 through 4, you're going to increase the centripetal force. You're going to keep the mass and radius constant. You should see an increase in your velocity. Okay? So down here on the bottom of page 1, I don't want to see all 12 trials worth of calculations. But I do want to see all of the calculations for trial 1. Okay? And again, when I say show the calculations, I do not mean writing down the formula. V equaling 2 pi r over t is not showing your work. You just wrote down a formula. I don't know what you put into it. I don't know how you got your answer. If you want, I highly recommend that you write that, but that isn't showing your work. You have to show the numbers that generate those values. Okay, so on 1 through 4, here's what's going to happen. Keep the radius the same, the mass of the stopper, increase in centripetal force. Now, on 5 through 8, we're going to change the radius, but we're going to keep the same centripetal force. So what's going to happen here is that you're going to go to the same setup, okay? And I've got a lot of string. String is cheap. So what you want to do on that one is that personally, if it were me, I'd pick like either the 200 gram or the 300 gram mass. So on 5 through 8, here's what's going to happen. You're going to keep the centripetal force constant, and that's going to equal mv squared. So on 5 through 8, the centripetal force is going to remain constant. Pick one, 0.2, 0.3, whatever. okay? Pick one, keep that the same. You're not gonna change the mass of the stopper. That's a fixed value.
Yes. Wait, C. B.
You're gonna change the radius. So this is where it's a little bit tough in terms of marks. When you change the radius, you need at least 10 to 15 centimeters between each interval. So you could start with like a small radius of say 0.5 meters. So you could lay this out, make this 0.5 meters. Take a mark, boom, put that there. So what I would do is I might use like different colors. So you've got like, for example, if I can get that off. God, that was tough. So you might lay this out, hey, there's 0.5 meters, and then you put that mark there as using like the black Sharpie. So then, but then down here, I've got a different color. Then I've got like a blue one here. So if I know this is gonna be, basically the different radius is gonna correspond with different colors on the mark. Now, if that gets confusing, just start with a new string and put like a new set of marks on it, okay? So here's what you've got, is that it's the same idea. You're gonna put that up, boom. I know I want that to be 0.5 meters. I'm gonna spin that around until that mark is at the bottom, boom, there's my radius. I know that mark. Do the trials. Then I might go to 65 centimeters, and then I might go to 80 centimeters, and then I might go to whatever, okay? But you want at least 10 to 15 centimeters change in between those radii. So let's think this through. So your centripetal force on 5 through 8 is going to remain constant. You're going to have the same weight hanging down. You're going to have the same mass of the stopper, not going to change. So, Gavin, as the radius gets bigger, to create the same centripetal force, what has to happen to your velocity?
It's gotta go down. Right? Oh, it's gotta go up. Because it has to match the radius and cancel out to keep the same force.
So as the radius gets bigger, your velocity has to get bigger because you want the same centripetal force. But is it going to change in a 1-to-1 ratio?
No.
Why not?
It's squared.
Because you have velocity squared. Okay? So as the radius gets bigger, you should see a bigger velocity. But the velocity is squared. So the velocity doesn't have to change as much because that's squared. Okay? So on that one, on that second set of trials back here, here's the second graph that you're going to draw. You're going to put radius on the x-axis, and then you're going to put velocity on the y-axis. Why don't you want to plot centripetal force on trials 5 through 8?
Because it should be the same.
Yeah, it's constant values. Like why plot centripetal force? Centripetal force is the same on all of them.
Yes.
Okay, now on trials 9 through 12, you're going to keep the same centripetal force on 9 through 12. You're going to keep the same centripetal force. You're going to keep the same radius. Okay, so now you're going to pick a radius. I don't care what the radius is, pick one. Pick one that speaks to you. Then you're going to change the mass of the stopper. You can start with the really small. I've got different size stoppers. You can start with the small, get bigger and bigger and bigger. I'm going to have an electronic scale in the back. That's how you're going to find the mass. Put it on there, boom, it's going to measure in grams. So you need that number. So then move to a bigger size. If you want to, you can even tie like different stoppers together. But if you're going to tie different stoppers together, you have to remember that you're measuring from the center of mass of the stopper to the edge of the tube. So that might alter your radius if you do that. Okay, so just be aware of the fact that if you do that, you might have to change where that mark is on the string. So, we're gonna start this today. We won't have a prayer of getting done. If you can get trials 1 through 4 done, and maybe get into 5 through 8, that would be great. And then we'll finish this all up on Monday.
Oh my gosh.
So you won't have any homework over the break.
Oh my gosh.
I can give you homework if,
Oh,
okay. All right, make it happen.
The reference